Welcome to Ultimate Sleep Doctor. Tonight, we'll journey to a place of endless wonder. The Milky Way, a river of light stretching across the vastness of space. Billions of stars, each a sun in its own right, swirling together in a graceful dance. It's a breathtaking spectacle, a testament to the immense scale of the universe and the quiet power of cosmic creation. Consider this: our own existence, a tiny spark within this grand, ancient system. There's a profound peace in recognizing our connection to something so much larger than ourselves. Let's allow ourselves to feel the stillness of space, the timelessness of creation. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe and let your thoughts drift. Allow yourself to sink deeper into comfort. Let's begin. Long ago, before our sun, before our solar system, even before the heavier elements were made of, the Milky Way wasn't quite the graceful spiral we see today. It began as a turbulent, chaotic cloud of gas and dust, a vast, swirling disk, much like a cosmic frisbee. This primordial disk wasn't perfectly flat. It was incredibly thick, perhaps 1,000 times wider than our sun is across. It was a place of immense gravitational interactions, a constant dance of particles pulled and pushed by unseen forces. The key to understanding the formation of this disk lies in the concept of hierarchical structure formation. Essentially, the universe began remarkably uniform, but tiny density fluctuations, minuscule differences in the distribution of matter, existed even in the very early universe. These tiny ripples, amplified over billions of years through gravity, served as the seeds for larger structures. Gravity, acting on these slight overdensities, began to pull in more and more surrounding gas and dust. As more material accumulated, these regions grew denser, becoming gravitational wells that attracted even more surrounding material. This process of accretion, the gradual accumulation of matter, was overwhelmingly dominant. The initial, relatively uniform cloud began to fragment and collapse under its own gravity. This fragmentation wasn't a single, dramatic event, but rather a prolonged, cascading series of collapses, with smaller fragments merging to form larger and larger structures. Now let's talk about the spiral arms. These beautiful, curving features aren't static, fixed structures. They're formed by a process called density waves. Imagine a line of people walking along a beach. As the line moves forward, it creates a wave that pushes the people ahead of it slightly. Similarly, as the galactic disk rotates, density waves, regions of slightly higher density, ripple outwards, compressing the gas and dust in their path. These density waves don't actually move through the disk. Instead, they are a wave of higher density that propagates along the rotating disk. As a wave passes through a region, it compresses the interstellar gas and dust, causing it to become brighter and more visible. This increased brightness is what we interpret as the light of the spiral arms. The waves then continue their journey, creating new regions of compression and brightness. The remarkable flatness of the Milky Way's disk is another consequence of this ongoing process of accretion. As material fell inwards, it wasn't simply adding to the thickness. It was preferentially drawn towards the mid-plane of the rotating disk. This resulted in a gradual, self-organized flattening of the structure over billions of years. Furthermore, interactions with smaller galaxies, galactic mergers, played a vital role. These mergers disrupted the disk, injecting fresh gas and dust and further shaping the spiral arms. The gravitational interactions created stretches and distortions within the disk, contributing to the complex structure we observe today. The formation of the Milky Way's disk wasn't a quick, single event. It was a long, slow, and complex process driven by gravity, density fluctuations, and the ongoing dynamics of a rotating, merging system. It's a testament to the power of small differences, amplified over vast stretches of cosmic time, that ultimately gave rise to the majestic spiral galaxy that houses our own solar system. Deep within the heart of our Milky Way galaxy, far beyond the swirling arms of stars and gas, lies a secret, a truly immense and powerful one. For decades, astronomers have suspected its presence, piecing together clues from subtle movements of stars and the intense radiation emanating from a single point. Finally, we've begun to truly understand it: a supermassive black hole residing at the very center of our galaxy. This black hole isn't just any black hole. It's Sagittarius A, short for Sagittarius A star, and it's an astonishingly large object. Its mass is estimated to be around 4 million times the mass of our Sun, crammed into a space smaller than our solar system. That's like taking the mass of every known star in the Orion Nebula and squeezing it into a point smaller than a city. Black holes, as you know, are formed when massive stars collapse at the end of their lives, but Sagittarius A is far beyond the life cycle of a typical star. It's a relic, a survivor from the early universe, likely formed billions of years ago. What makes Sagittarius A particularly fascinating is its influence on the stars that orbit it. These stars don't follow neat, predictable paths like planets around our Sun. Instead, they dance in incredibly tight, complex orbits, whipped around the black hole at astonishing speeds, some reaching nearly a third of the speed of light. Astronomers have been meticulously tracking these stellar movements, observing the wobble of these stars, to directly confirm the black hole's existence and measure its mass with incredible precision. These observations were crucial, providing the first direct evidence of a supermassive black hole at the Milky Way's center. The gravity of Sagittarius A isn't just affecting the stars. It's also influencing the entire galactic center. It's believed that the black hole plays a key role in regulating the growth of the Milky Way itself. Scientists theorize that Sagittarius A periodically sends out powerful jets of energy and matter, streams of particles traveling at near-light speed, extending for thousands of light-years into space. These jets interact with the surrounding gas and dust, potentially fueling star formation or disrupting existing structures. Furthermore, Sagittarius A contributes to the overall dynamics of the galactic bulge, the dense, peanut-shaped regions surrounding the black hole. The gravitational pull of the black hole, combined with the gravitational forces of the stars and gas in the bulge, creates a complex and dynamic environment. The black hole itself doesn't actively pull everything in. Rather, it's the dominant gravitational force within a vast region, shaping the evolution of the galaxy around it. Recently, the Event Horizon Telescope, a global network of telescopes, captured the very first image of Sagittarius A. It revealed a blurry, orange-colored ring, the shadow of the black hole itself, created by the extreme warping of light around its immense gravity. This image was a monumental achievement, confirming our theoretical understanding of black holes and providing an unprecedented glimpse into the heart of our galaxy. It's a testament to the ingenuity and perseverance of scientists working to unlock the universe's deepest secrets. Ongoing observations continue to refine our understanding of Sagittarius A, its impact, and its role in the grand cosmic story of the Milky Way. As technology advances and new data is gathered, we'll undoubtedly learn even more about this mysterious and powerful object, further illuminating the intricate workings of our galaxy. Deep within the swirling arms of the Milky Way, a constant miracle is unfolding: the birth of stars. It's not a sudden explosion, but a slow, deliberate process, beginning with vast, cold regions of space called molecular clouds. These clouds aren't empty. They're brimming with gas, primarily hydrogen and helium, along with tiny amounts of heavier elements like carbon and oxygen. They're incredibly dense, much thicker than anything we experience on Earth, and often span light years across truly enormous collections of material. These clouds aren't uniform. They're often threaded with filaments like cosmic silk and contain denser knots within them. These knots are the key to star formation. Gravity, that familiar force pulling things together, begins to work its magic within these denser regions, causing the gas and dust to slowly collapse inwards. As the material compresses, it heats up. This increasing temperature is a critical step, and it's driven by the conversion of gravitational potential energy into thermal energy, much like squeezing a balloon makes it warmer. As a denser region within a molecular cloud continues to collapse, it forms a core, a particularly concentrated clump of gas. This core becomes increasingly unstable, and the inward pull of gravity accelerates. The core begins to fragment, breaking apart into smaller, denser clumps. Each of these clumps will eventually become a star. Within these clumps, the gas and dust swirl around, gradually forming a rotating disk around a central point. This disk is called an accretion disk, and it's where most of the star's initial mass will come from. At the very center of this accretion disk, the material continues to accumulate, growing hotter and denser. The pressure and temperature at this core reach incredible levels, eventually triggering a runaway nuclear fusion reaction. Hydrogen atoms begin to smash together with immense force, fusing to form helium and releasing an enormous amount of energy in the process. This is how a star is born. The newly formed star, still wrapped in the remnants of its accretion disk, begins to shine brightly, pushing away the surrounding gas and dust. This process illuminates the surrounding molecular cloud, creating a stunning sight. The ejected material forms a beautiful, expanding shell called a planetary nebula, while the remaining core becomes a white dwarf, a small, incredibly dense star that slowly cools over billions of years. The entire cycle, the collapse of a molecular cloud, the formation of a star within an accretion disk, and the eventual dispersal of material as a planetary nebula, is a remarkably efficient process. It's estimated that new stars are being born in the Milky Way at a rate of roughly 1 to 5 per year, continuing the galaxy's grand story of creation. These newborn stars, twinkling amongst the ancient light of older generations, are the future of our galaxy. The swirling, luminous disk of the Milky Way, which we've been exploring, isn't the entire story of our galaxy. Extending far beyond the bright, rotating disk is a vast, diffuse shell, the Milky Way's halo. It's a surprisingly large region, encompassing perhaps 5 times the diameter of the disk, and it holds some of the galaxy's most intriguing and mysterious secrets. Much of what exists within this halo remains unseen, largely because it's composed primarily of dark matter. This elusive substance doesn't interact with light, making it invisible to our telescopes. However, its gravitational effects are undeniable, influencing the motion of stars and the distribution of galaxies throughout the halo. Scientists believe dark matter makes up roughly 85% of the halo's mass, a staggering proportion that highlights just how much we still don't understand about the universe. Within this dark matter float countless globular clusters. These are ancient, tightly bound groups of hundreds of thousands, or even millions, of stars. They're like tiny, dense islands of stars orbiting the Milky Way with remarkable regularity. Many globular clusters are incredibly old, dating back to the early formation of the universe. Some may be among the very first star systems to emerge. Their stellar populations are typically red and yellow, reflecting their age and the fact that massive, bright stars have long since burned out. Studying their orbits and compositions provides vital clues about the Milky Way's past and the processes involved in its initial assembly. Furthermore, some globular clusters appear to be captured members of other, now-defunct galaxies, offering a snapshot of galactic mergers that shaped the Milky Way's evolution. Adding to the complexity of the halo are the stream galaxies, faint, elongated trails of stars and gas stretching for tens of thousands of light years. These aren't independent galaxies themselves, but rather the remnants of galaxies that have been torn apart and absorbed by the Milky Way's gravity. These tidal streams are evidence of the Milky Way's constant growth, a galactic cannibal. As the Milky Way has moved through the universe, it has swept up smaller galaxies, disrupting their structures and leaving behind these stretched-out filaments of stars. Astronomers can identify these streams by analyzing the velocities and compositions of the stars within them, allowing them to trace the pathways of these past galactic encounters. The distribution of stars within the halo isn't uniform either. There are denser regions and more sparsely populated areas, influenced by the distribution of dark matter and the gravitational pull of the Milky Way's central supermassive black hole. Looking out into the halo, we observe a characteristic cusp, a denser concentration of stars near the galactic center, gradually tapering off as we move outwards. This shape continues to be refined with increasingly sensitive observations, providing a deeper understanding of the complex gravitational forces at play in our galaxy's outer reaches. The study of the halo is not merely about understanding the edges of the Milky Way. It's about unraveling the story of its entire existence, from its birth to its ongoing evolution. The Milky Way isn't just a beautiful spiral of stars. It's also permeated by a surprisingly powerful magnetic field. This field, far from being a simple, uniform shield, is incredibly complex and plays a vital role in shaping the galaxy's evolution. Its origins are still being actively researched, but the prevailing theory revolves around a process known as a galactic dynamo. Think of it like a giant, cosmic whirlpool, constantly generating and organizing the magnetic field lines that stretch across vast distances. The basic idea is that swirling gas and dust within the Milky Way, particularly the hot, ionized gas that makes up the galaxy's interstellar medium, are the key ingredients. This gas isn't static. It's constantly moving in a chaotic dance, driven by the gravitational pull of the galaxy's stars and the differential rotation, where stars closer to the galactic center orbit faster than those farther out. This differential rotation creates what scientists call shear within the gas, essentially a twisting or shearing effect. This shear is critical. It's like taking a piece of cardboard and twisting it. The twisting motion induces a current within the material. Similarly, the shearing motion of the interstellar medium generates an electric current. And crucially, electric currents create magnetic fields. This is a fundamental law of electromagnetism. The turbulence itself, the chaotic swirling of the gas, acts as the conductor, carrying the electric current and amplifying the magnetic field. However, the dynamo isn't just a simple one-way process. The magnetic field doesn't just passively respond to the gas motions, it actively influences them. The magnetic field lines exert a force on the moving gas, channeling its flow and concentrating it in certain regions. This creates stronger turbulence, which in turn strengthens the magnetic field, creating a positive feedback loop, a self-sustaining dynamo. It's a beautiful, intricate dance of energy and magnetic fields. Scientists use several techniques to study this galactic dynamo. Radio telescopes, like the Westerbork Synthesis Radio Telescope and the Very Large Array, are particularly powerful tools. These telescopes detect the polarization of radio waves emitted by the interstellar medium. Polarization occurs when electromagnetic waves, like radio waves, are affected by the magnetic field, causing them to vibrate in a preferred direction. By analyzing the patterns of polarized radio waves, astronomers can map the strength and direction of the magnetic field at different locations throughout the galaxy. Furthermore, observations of polarized light from distant quasars, incredibly bright and energetic objects, provide another window into the Milky Way's magnetic field. The light from these quasars is bent and distorted as it passes through the galaxy's magnetic fields, revealing the field structure on a grand scale. The subtle variations in this polarization provide a wealth of information about the dynamo's workings, revealing the complex interplay between rotation, turbulence, and magnetic fields that defines the very heart of our galactic home. Understanding this dynamo is a key step in unlocking the full story of the Milky Way's formation and evolution, and its continuing journey through the cosmos. The Milky Way isn't a static, isolated island in the vast darkness of space. It's a remarkably active participant in a cosmic dance, constantly interacting with its neighbors. For billions of years, the galaxy has been swept up in a series of gravitational encounters, sometimes gentle nudges, sometimes dramatic collisions, all of which have profoundly shaped its structure and evolution. These interactions aren't just accidental bumps, they're a fundamental part of how galaxies grow and change. One of the most significant of these encounters was with the Sagittarius dwarf spheroidal galaxy. This small galaxy, once a full-fledged spiral, was gradually torn apart by the Milky Way's gravity, a process known as tidal disruption. As Sagittarius approached, the Milky Way's immense gravitational pull stretched and distorted its stars, creating a beautiful, long stream of stars, the Sagittarius stream, that now arcs across our halo. This stream isn't just a remnant, it's a tangible consequence of a past encounter, a record etched in light. But the story doesn't end there. The Milky Way is currently engaged in a particularly intense interaction with the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These two dwarf galaxies are orbiting the Milky Way, spiraling closer and closer over hundreds of millions of years. The LMC, in particular, is experiencing significant tidal distortions, creating its own stellar streams that mingle with the Sagittarius stream. These streams are incredibly rich in young, hot stars, born from the compression of gas as the LMC is pulled and stretched. These mergers aren't just about the individual galaxies losing their shape. They're about the fundamental building blocks of the Milky Way being stirred up and redistributed. The gravitational forces involved heat up the gas and dust, triggering bursts of star formation, often intense and dramatic events that we observe as tidal tails, extended streams of stars trailing behind the merging galaxies. The energy released during these events influences the dynamics of the entire system, creating ripples of gravitational waves that propagate through space. Scientists are particularly interested in understanding how these interactions contribute to the formation of our own galactic bar. The Milky Way possesses a prominent bar-shaped structure across its center, thought to be formed through the repeated gravitational disturbances caused by past mergers. These events have channeled gas and dust towards the galactic center, fueling the intense star formation we see in the central bulge. Furthermore, the ongoing interaction with the LMC is predicted to eventually result in a full merger, where the LMC will become a permanent part of the Milky Way's halo, contributing to its overall mass and complexity. This future merger will undoubtedly reshape the galactic center and potentially trigger even more bursts of star formation. The Milky Way's history, then, isn't just a story of its own birth, but a chronicle of countless meetings and transformations, a testament to the dynamic nature of galaxies in the universe. The Milky Way, as we've come to understand it, isn't a uniform place. It's far more complex, layered like a delicious cake with distinct flavors and textures. One of the most fascinating aspects of this complexity lies in what scientists call the metallicity gradient. This describes a very subtle but incredibly important difference in the composition of stars as you move outwards from the galactic center. Initially, when the universe was very young, everything, all the stars, were made of hydrogen and helium, the simplest elements. These first stars, born from the leftovers of the Big Bang, were incredibly massive and burned brightly, but their lives were short and explosive. They ended their existence in spectacular supernovae, scattering heavier elements like carbon, oxygen, and iron out into space. These heavier elements, forged in the hearts of those ancient stars, became the building blocks for subsequent generations. But these new stars formed in regions where the density of these newly released elements was lower. Consequently, the stars born further away from the galactic center, in the outer spiral arms and the halo, were noticeably poorer in metals compared to the stars closer to the Milky Way's core. We call these elements metals because they are all elements heavier than hydrogen and helium. It's a bit of a misleading term, as some of these elements, like iron, aren't actually metallic in the same way as the metals we find on Earth. However, the concept is useful for describing the abundance of these heavier elements in stellar atmospheres. This difference in metallicity has a profound effect on the types of stars that can form. Younger, metal-rich stars tend to be hotter and bluer, while older, metal-poor stars are cooler and redder. The galactic center, having been the site of intense star formation for billions of years, is dominated by these bright, blue, metal-rich stars. As you move outwards, you gradually encounter more and more red, metal-poor stars, particularly in the halo. Scientists study the light from these stars, carefully measuring the amounts of different elements present to piece together the story of the Milky Way's chemical evolution. It's like examining the ingredients in a recipe to understand how it was made. The metallicity gradient provides crucial evidence for the idea that galaxies grow through a series of star formation episodes, each enriching the interstellar medium with heavier elements. Furthermore, the distribution of these metal-poor stars, especially those in the halo, provides clues about the Milky Way's past mergers with smaller galaxies. These mergers would have brought in fresh supplies of gas and dust, effectively restarting the process of star formation and adding even more metals to the galactic mix. Understanding this metallicity gradient is therefore key to understanding the entire history of our galaxy, from its earliest formation to its current complex structure. Let's turn our attention now to a question that has captivated humanity for centuries. Are we alone in the Milky Way? For many years, the search for life beyond Earth was largely theoretical, but recent discoveries have transformed it into a vibrant and intensely active area of scientific research. The sheer scale of our galaxy, containing perhaps hundreds of billions of stars, dramatically increases the probability that other planetary systems exist, and potentially that some of those systems harbor life. The starting point for this search is understanding where life might be able to thrive. Astronomers have identified a concept called the habitable zone around a star. This zone, often referred to as the Goldilocks zone, isn't about finding planets made of gold. It's about identifying the region where a planet's temperature could allow for liquid water to exist on its surface, a crucial ingredient for life as we know it. Water, in its liquid form, acts as a solvent, facilitating the complex chemical reactions needed for life. The location of this zone depends on the star's size and temperature. Hotter, brighter stars have wider habitable zones, while cooler, dimmer stars have more compact ones. The discovery of exoplanets, planets orbiting stars other than our Sun, has been a truly revolutionary moment. Initially, finding exoplanets was incredibly challenging, but missions like the Kepler Space Telescope and now the James Webb Space Telescope have allowed us to detect thousands of them. These telescopes use various techniques, like observing the slight dimming of a star's light as a planet passes in front of it, the transit method, or measuring the wobble of a star caused by a planet's gravity. We're finding planets of all shapes and sizes, some rocky like Earth, others gas giants like Jupiter, and many more with characteristics we're still working to understand. However, finding exoplanets in the habitable zones is just the first step. We need to analyze their atmospheres to look for biosignatures, chemical indicators of life. Scientists are searching for gases like oxygen, methane, or other compounds that would be unlikely to exist in large quantities without a biological source. This is incredibly complex, requiring powerful telescopes and sophisticated data analysis. Despite these exciting discoveries, a fundamental question remains. If the Milky Way is teeming with potentially habitable planets, why haven't we detected any evidence of extraterrestrial civilizations? This is the heart of the Fermi paradox. Proposed by physicist Enrico Fermi, it asks, given the high probability of extraterrestrial life, why haven't we found any signs of it? There are numerous potential explanations, ranging from civilizations deliberately avoiding contact to technological limitations that prevent us from detecting them. Or perhaps the galaxy is simply a lonely place. Perhaps advanced civilizations exist, but operate on timescales far longer than our own. Or perhaps they've simply moved beyond the need for physical communication. The search continues, fueled by curiosity and a deep-seated desire to understand our place in the vastness of the Milky Way. It's a quest that demands patience, ingenuity, and a willingness to consider even the most extraordinary possibilities. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds one peaceful night at a time. Gazing upon the Milky Way, a river of stardust has painted the canvas of your dreams. Let your thoughts drift now, calm and unhurried, like distant constellations. Allow the peace of the universe to settle within you. Good night.